Good morning. Today we're going to be talking about something called L'Hopital's rule. And this guy's French, so of course his name is hard to pronounce, but just remember it's French, so leave out all of the letters. So we get the L and we get an O, Pital, so L'Hopital's rule. We're going to come back and visit our idea of finding limits. In chapter 2, we discussed limits a lot. In fact, nearly the only thing we did in chapter 2 was limits, but not exhaustively. We didn't beat a dead horse. And some limits pose greater challenges than others, like the limit as x approaches 0 of sine of x over x, or the limit as x approaches infinity of x over x plus 1. Simply plugging in our values for a left us with either 0 over 0 or infinity over infinity, respectively, which are called indeterminate forms. And that means that they don't mean anything. 0 over 0 doesn't mean anything, and neither does infinity over infinity. You need special techniques to determine what the value of our limit is. And a particularly powerful technique is L'Hopital's rule, which we're going to get in right now. So suppose f and g are differentiable functions on an open interval I containing a point a with g prime of x not equal to 0 on I when x is not equal to a. That means when we take the derivative of g, it doesn't equal 0 anywhere on the interval except maybe at a. If the limit as x approaches a of f of x and the limit as x approaches a of g of x both equal 0, then we can say something really cool. We can say that the limit of the ratio of those two functions as x approaches a is equal to the limit of the ratio of their derivatives as x approaches a, provided that the limit on the right exists. And this rule also applies if x approaches a is replaced with x approaches plus or minus infinity, x approaches a from the left, or x approaches a from the right. So let's go ahead and see an example. That way you guys can really get this in. Let's start with evaluating the following limit. We've got the limit as x approaches 1 of x cubed plus x squared minus 2x, all over x minus 1. If we plug in our a value, we get 1 plus 1 minus 2, which is equal to 0, over 1 minus 1, which is also equal to 0. So we have something that looks like 0 over 0. So we need to do something else. And we could try factoring. That's always a good trick that you can do when you've got a polynomial on top and a polynomial on the bottom. But factoring can be pretty cumbersome, especially when you have an x cubed or maybe x to the fourth, x to the seventh term in the numerator. Those get pretty difficult to factor pretty quickly. So let's use something else, namely L'Hopital's rule. So to evaluate the following limit, we first start by determining our f of x and our g of x. And our f of x is equal to our numerator, so x cubed plus x squared minus 2x, and our g of x, which is x minus 1. And we take the derivatives of each. So f prime of x is 3x squared plus 2x minus 2, and g prime of x is equal to 1. Now we know that g prime of x does not equal 0, which is exactly what we need for this to work. And we know that both are differentiable, so we're doing great so far. Next, we set up our new limit. So our original limit now becomes the limit as x approaches 1 of 3x squared plus 2x minus 2, all over the value 1. We plug in 1 in the numerator, and we get 3 plus 2 minus 2 over 1. So 3 over 1 equals 3. And boom, we found a number. And if you want to check our original function, our original limit by factoring, you'll get the exact same answer. So let's check. We saw something that said 0 over 0. Let's check the graph and see that it truly does equal 3. Here I've got a graph of our function, and we can see as we approach 1 from the left and from the right, we get closer and closer to a value in between 4 and 2, which is exactly 3. And that is exactly what we want. So the graph agrees with what L'Hopital's rule agrees with. We know that L'Hopital's rule is valid without going through a big cumbersome proof. So let's try another example. I want you guys to evaluate the following limit using L'Hopital's rule, and it's the limit as x approaches 0 of quantity 9 plus 3x square root minus 3 all over x. So go ahead and try this one on your own. I'm not going to show you the answer to this. I just want you guys to try it. That way you'll see what we get out. Hint, your answer should be 1/2. So see if you can't get that. So we're still talking about L'Hopital's rule, and this is a very special case. So when we go to evaluate the following limit, the limit is x approaches 0 of e to the x minus 1 over x squared. The limit has the indeterminate form 0 over 0. So we have to use L'Hopital's rule, which gives us the limit as x approaches 0 of e to the x minus 1 over 2x. And if we plug in 0, we get 1 minus 1 over 0, which equals 0 over 0, which means we've run into another problem. But the cool thing about L'Hopital's rule is that we can just apply it a second time. We check that our denominator, when we take the derivative, equals 2, so it doesn't equal 0, and we actually can differentiate the numerator and the denominator again. So we check those things, we go ahead and we take the derivatives, and we're left with the limit as x approaches 0 of e to the x over 2. Plug in 0, we get e to the 0, which is 1 over 2. Our answer is 1/2. So you can apply L'Hopital's rule as many times as you need, as long as you meet the requirements. So you're checking for differentiability, you're checking to make sure that g prime of x does not equal 0 on your interval, and you're making sure that you're actually getting an indeterminate form. That's to say, x over x, you could differentiate and get 1 over 1, but there's no need to differentiate again. You're just getting the value 1. So what about the case when we get infinity over infinity? So suppose f and g are differentiable on an open interval I containing a point A with g prime of x not equal to 0 on I when x is not equal to A. If the limit as x approaches f of x and the limit as x approaches a of g of x both go to positive or negative infinity, then the limit of the ratio of those functions is equal to the limit of the ratio of their derivatives, provided the limit exists. And the rule applies for x goes to positive and negative infinity, x goes to a from the left, and x goes to a from the right. So go ahead and try the following example. First, verify that the following limit results in an indeterminate form, and then use L'Hopital's rule to evaluate the limit. Remember, we could use our limit techniques and say we've got leading coefficients and compare those. So x cubed over x cubed, we just take the leading coefficients, so 4 over 2, all equals 2. Or we could use L'Hopital's rule to prove that this is the same answer to get 2. So go ahead and try this example and check Bryce's video, and he'll do the full work through.